Section 3.6 is about a really important topic that will come back to visit you throughout all of college algebra, and the topic is functions. In order for me to define functions, I have to start out by defining in math what's called a relation. And a relation is a set of ordered pairs. Now, if I were to draw you or write an example of a relation, it's a set, so I'm going to use the symbol. Whoops, kind of messed that up. Let me try it again. The symbol for sets, and I will include in this set a bunch of ordered pairs. So how about 5, 2, 6, 3, 9, 7. That's a set or a collection of ordered pairs. Now, something that you notice about ordered pairs, and you remember from another class, they are x's and y's. So sometimes a relation is defined to be, and I'm not going to write this down, but I'm going to just say it. It is a correspondence between members of two sets. So it is a correspondence between x's and y's. An x and a y, they come together, they make an ordered pair, you get a group of them, you just built a relation. Some people might want to call it a relationship between x's and y's, okay? Now, you could have it written horizontally. It could be written as a T-chart. I could have 2 with 3, 5 with 9, 8 with 7. And that would be a relation also, a set of ordered pairs, a correspondence between the x's and the y's. It could be formally written. You'll see this more in college algebra. The set of all x, y's such that. Now, this language, this is set notation, and it says the set of what's? Well, it's a set of x, y's. It's a set of points such that y equals 2x plus 1. In other words, it is all ordered pairs which make this equation true. This is the part of the set of the notation that's really important. And what would that look like? Well, it would be a set of points. If I let x be 1, what would y be if you plugged in 1 for x? 2 times 1 is 2, plus 1 is 3. So that would be a point of that relation. What if I let x be 5? What would y be? 11. It would be 2 times 5 is 10, plus 1 is 11. And ... there'd be an infinite number of ordered pairs that could be filled in there. So in other words, going back, a relation is a set of ordered pairs. Could be written like this, a listing. Could be written as a T-chart. I could instead give you an equation, and that implies that there are ordered pairs that satisfy it. And finally, for a relation, I could draw you the graph. What if I had this? Does this picture define a relation for you? Is that a collection of ordered pairs? Well, does every point represent an x, comma, y? Yes, so that would describe a relation. Now, the relation graph might be something you're more familiar with, like a line. And today, after we finish with 3.6, we jump to 8.1 where we study more about linear functions. Okay? Now, and I probably should have started out saying this. We did chapter 6, we did chapter 7, and then seeming like I lost my mind, I went back and grabbed section 3.6. Well, I wanted to go back and review, or maybe talk about for the first time, functions before we get into linear functions. So I have backtracked on purpose. If anything that I talk about in this entire unit gets a little confusing to you because you don't have a fresh background, you would want to go back to about section 3.4 and 3.5 and maybe review. Maybe read through the text, maybe watch the videos, but go back to those. So we have a relation. It's a set of ordered pairs. It is a correspondence. It is getting an X together with a Y. I want to define two words for you. Domain. Hopefully we're familiar with domain. You actually had a question on your last test about domain. It is the set of X's in a relation. The range is the set of Y's in a relation. If you think about that alternate definition that I gave you, that a relation is a correspondence between, it's a set of correspondence between members of two sets. Well, you take a member from the domain, you take a member from the range, you join them together in an ordered pair, you do that several times, you create a relation. Okay, so the domain is the X's and the range is the Y's. Now, finally, I'm going to define the word function, which is where I started this discussion. A function is a type of relation in which each X corresponds to only one Y. It's a type of relation in which each X corresponds to only one Y. Now, in a relation, there are no rules between X's and Y's. You just need to get an X attached to a Y, do that a few times, and you've just built a relation. If you put a rule on the X's, you can create a relation which is called a function. Now, I'm going to give you some examples of relations, and I want you to tell me whether they are functions or not functions. And, whoops. We're going to use this rule. And I'm going to give you kind of a silly analogy to help you understand it. This can be a little bit abstract, but I'm going to give you an analogy that, silly as it may be, should help. Okay, a relation. Correspondence between an X and a Y. An X and a Y getting together. Well, if you've had just a teeny tiny bit of genetics, or maybe just some plain old biology, you know that X chromosomes tend to be related to females and Y chromosomes tend to be related to males. Okay, so a relationship. We're going to get an X, a lady, together with a Y, a gentleman. Okay, so we're going to get an X and a Y together. The relationship is going to be categorized as a function if the lady is faithful to her man. Okay? If the X is faithful to the Y, then it's a function. Did I say anything about the Y's? No. we are not going to even notice what the Y's are doing. They can do anything they please. I'm not promoting this kind of relationship. I'm just telling you it's the definition of a function. Only the ladies are held accountable for what they do. Okay? By the way, just for the ladies in the audience, if you're worried about this, if you take college algebra, you will go on and study a special kind of function where not only are the ladies faithful to their men, but the men are faithful to their ladies. And it's called a one-to-one function. In our life, we might call it marriage. Or not, I don't know. Okay, so, but for now, we're just watching what the ladies are doing. So, function or not a function? Here we go. Let's suppose that I give you a relation, and it is 5 with 2, 6 with 9, and 8 with 3. That's a relation. Is it a function? Well, just check on the ladies. Check on the X's. Little Miss 5 is out with Mr. 2, and she doesn't go out with anybody else. Miss 6 is out with Mr. 9, and she doesn't go out with anybody else. Miss 8 is out with Mr. 3. She's faithful to him. What do you say? It's a function. Okay, let's look at another relation. Let's look at 5, 2, 6, 9, 8, 9. It is a relation. Is it a function? Okay, how do we test? We look at our ladies. The ladies are the X's. Miss 5, she's out with Mr. 2. She didn't go out with anybody else. Miss 6 is out with Mr. 9, and Miss 6 doesn't go out with anybody else. Miss 8 is out with Mr. 9. She doesn't go out with anybody else. Mr. 9 is a scumbag. But you know what? We're not looking at the Y's. So it's a function. I'm sorry about what Mr. Y is doing. I have personal views about that, but it's not in the definition of a function. We're only checking on the X's. All right, what about 5, 2, 6, 9, and 5, 8? Oh, we are making some noise about this, because what's going on? 5 is a floozy. When the X is repeated, and she's going out with Mr. 2 on Monday, and she's going out with Mr. 8 on Thursday, it's not a function. Not a function because your X was messing around. Okay, now I know that that's a silly analogy, but I have learned over the years that if you can make something attached to something you already know in your brain, then it's going to stick a whole lot better. All you're checking on are the X's. If the X repeats, she's messing around, it's not a function. Okay? Now, it's pretty easy to tell if something is a function or not when you're looking at the ordered pairs. But what if you're looking at the graph? Can you tell? Well, you can. It's still relatively easy, but I need to remind you of something. This is, and I am going to do this a whole bunch in today's lesson. I'm going to recall things from Math 307. Okay, do you remember what x equals, let's just say 2, looks like as a graph? Which axis does it cut through? The x-axis. This is the line x equals 2. It is a vertical line. When you're talking about a vertical line and it says x is 2, I want you to think about some of the points that are on that line. Do you agree that the point 2, 0 is on that line? How about the point 2, 1? And the point 2, negative 5? And 2, 17? Are they all on that line? would you say that that line is a function or not a function? Not a function. That is definitely not a function. I'm going to use the vertical line as a test to see if other graphs are functions. So let me show you how I'm going to do that. So that really should not have been marked as an example. That was just a remember. I wanted you to think about vertical lines. Let's suppose that I have this graph of this slanted line, and I ask you, is that a function? Well, here's the way that you use the test. You take an imaginary vertical line, and you can pass it from left to right across your graph. Now, I only hit it with say 10 vertical lines, but let it just move continuously across. Every one of those vertical lines was an x equals. Did any one of them hit my graph in more than one place? Or did it intersect it just once each time? Just once. That means that when x is -5, there was one y value. When x is -4, there was one y value. This is called the vertical line test. Vertical line test. If passing a vertical line hits your relation in only one place, then it passes. That means that for each x, there was only one y value. This is a function. Let me show you something that's not a function. What if I have this graph? And I say, okay, is this a function or not? Well, start over here and start letting vertical lines, those are supposed to be vertical, even though I got a little crazy with some of them. For each of those vertical lines, and you only have to fail it once to fail, did a vertical line, which is an x equals, did it ever cross your relation in more than one point? Yes, it did over and over. I'm going to highlight just one example of where it failed. If this, and I'm going to make this up, if this happened to be the line x equals 3, would you agree that I have 2 points, that this one might be 3, 2, and this one down here might be 3, -2? And would that demonstrate to you that it failed being a function? Little Miss 3's going out with a couple of different y's. So you have failed the vertical line test because you crossed it twice. That is not a function. Passing the vertical line test means that every vertical line only hit it once. Failing the vertical line test means that a vertical line somewhere hit it 2 or more times. Is that okay? Passing, failing. All right. That was the vertical line test. Let's look at our problems now. I will try to enlarge this for the students present. Whoops. Okay. I may have to read it out to you. Problem number 1. It says, find the domain and the range. Okay, and in the instructions, it says, after it asks, whoops, that was supposed to be yellow. Find the domain, and it says use a comma to separate answers. So it's going to be just a listing that's going to go inside the box. So what is the domain? What would the list include? 8, -4, and -3. That list sitting in this set notation would be the domain. It is the set of x's. The second part of the question says, what's the range? Well, looking at these ordered pairs, what is the range? It's just -10. And although it is used 3 times, you don't list it 3 times. You just list it once if it's in there at all. And it doesn't ask this. I'm throwing out this question. Is this relation a function? Yes, because all you do is check on the x's. 8 is with -10, but 8 is never listed again as an x. -4 is with -10. -4 is never listed again. -3 is with -10. So if the x's are all distinct, it's a function. But that wasn't a question. But I threw it out there for fun. All right, let's look at number 2. It says determine if the given relation is also a function. So here they are. What do you check on? Just the x's. Do you see a problem? Yes. What's the problem? 7. Little Miss 7 is a repeated x value. So the answer is no. That is not a function because x can only have one y, and 7 goes with both -6 and 1. Not a function. All right, let's look at 3. Determine if this relation is a function. -8, 5, -8, 9, -8, 1. What do you say? Definitely no. -8 is kind of a floozy number. Okay, she's going out with all those different y's. So this is a no. No, we don't even care what the y's are to determine if something's a function. You're only checking on the x's to see if something is a function. Each x has to be distinct or different. Okay, now the next one, number 4, if you don't have this printed, it may be a little hard for you to write this down in notes. It says determine whether the given graph on the right is the graph of a function. All right, so I have it up here on the screen. What do we use to determine if a graph is a function? We need to use the vertical line test, the VLT. Okay, if I start passing vertical lines, okay, if I do this one, no problem. But what happens when I do this line? Do you see a problem? We've got that point and that point. Because the vertical line went through both of them, it means they had the same x. So that right away says that this is not a function. It failed the vertical line test. And so it says, is the given graph the graph of a function? My answer is no. Number 5. Somewhere. There it is. And it says, use the vertical line test to determine whether, and then it cuts it off, the graph is the graph of a function. And here's the picture. All right, do you say this is a function or not? It's not a function. If I use the vertical line test, now all you have to do is fail once. This one fails over and over. Any vertical line that cuts through one point of it looks like it's probably going to cut through 2 points of it. Well, actually, what if I had this as a picture? What if I had this picture, which we will graph at the end of our semester? Okay, would that pass the vertical line test? Yes, I can't seem to draw a vertical line to save my life, but if you could pretend that those are vertical lines, that would pass. That would be a function. And there's lots and lots of things that are functions and equal number of things that are not functions. Okay, so if I go back and try to answer this, is it the graph of a function? My answer was no. Problem number 6. It says, decide whether the equation describes a function. Now, this is the only one of these that we do. In college algebra, you do a lot of this with a lot of different kinds of equations determining if they're functions or not, but we just do this one. What do you know about this? What do you know about x equals -4? What do you know about its graph? It's what kind of line? It's a vertical line. So if I were to draw a picture of this, it would look like 1, 2, 3, 4. It would cut through the x-axis at -4. Is a vertical line going to pass or fail the vertical line test? It's going to fail it. It's going to fail it big time. If I do my vertical lines in red, or I try, what happens to the vertical line that actually intersects that? It intersects it everywhere. So it fails. It doesn't just fail because for each x there's 2 y's. For that x, there's an infinite number of y's. That is about the worst failure there could be. If that is the line x equals -4, think about the points on it. -4, 0, -4, 1, -4, 2, -4, -1. Little Miss -4 is busy. She is going out with every y there is. Okay? Fails. The answer is no. This is not a function. All right, one more time. We're going to look at a graph. This is number 7. And it says to use the graph to answer the following. Is the graph of a function? Between what? I just couldn't. Okay. On this picture, and it may be a little bit difficult to see, and if you printed it, I don't know how bad it might have come out. Some of these little segments have dots on the end, and some of them have holes on the end. And a hole on the end means it's not included, and a dot means it is. So let's use that to determine this weird little thing, is it a function? So I'll get my red line. Okay, if I start out on the left, it is busy passing the vertical line test right now. Now, right here, just look at that little region. Does it pass the vertical line test right there? Well, above I have a dot, which means there is a point. But below I have a hole, which means there is not a point. So isn't that okay? I didn't fail the vertical line test. And right here, I'm not going to fail the test. And then I go on, everything's cool. And right here, I'm not going to fail. And right here, I'm not going to fail. And I'm not failing. And I'm not failing. But what about right there? What happened right there? In fact, it happened right here for the first time. And it happens over and over in this little region. In that little region, which you can't even see anymore, but I failed the vertical line test. Let me just put 1 back in there. That's where it fails. And if you fail anywhere, you fail. It is not a function because for that x, there are two y's. Is that okay? Y'all are using your poker faces with me today. Okay. It would pass, yes. From that point on, you're exactly right. From that point on, it begins to pass again. But when I ask you, are you a function? If you fail it anywhere, you failed it. Okay? I just stopped there and said, I just found a point of failure. All right. We change gears a little bit, and I hope that this next part will look very familiar to you. We have done it. We certainly, those of you who are with me in Math 307, you did this, and we did a little teeny bit of it, I think. We talked about function notation when we were in Chapter 7. Okay, it says, given the following function, find, and up here in the instructions, although it got a little squished right here, find f of negative 4, f of 0, and f of 4. Okay. Function notation. If y equals 3x minus 3 is indeed a function, then the y can be called f of x. It's just a name change. Y is called f of x. F of negative 4 is, well, if I'm putting a negative 4 where x was in the name, then you plug in negative 4 for x as well. That is 3 times negative 4 minus 3. And then simplify. And we can simplify in our heads. 3 times negative 4 is negative 12. And negative 12 minus 3 is negative 15. Let's find f of 0. F of 0 means put 0 in for x. It's 3 times 0 minus 3, which is what? 3 times 0 is 0, minus 3 is negative 3. The last one, what is f of 4? Well, that's 3 times 4 minus 3. Well, 3 times 4 is positive 12, minus 3 is 9. Did this remind you a little bit of doing a T-chart where I'm giving you some x's and you're calculating some y's? We're just doing it in function notation. The next question, let's just do one part of it together. Number 9, we're given a different function and asked to find values. In this one, f of x, which is the same thing as y equals x squared minus 5. Okay, when you do this, if you happen to be using some calculator a sophisticated calculator, then f of negative 5, make sure you put that negative number in parentheses. That's going to be parentheses negative 5 squared minus 5. If you don't put it in parentheses, then your calculator will square just the 5 part and make it be negative. So, what is negative 5 as a base squared? 25. Minus 5 is 20. And you could get the wrong answer if you don't use parentheses and you used a calculator. And I'm assuming that you could finish that out just fine. Is that okay? All right. Problem number 10. It says, for the given function value, write a corresponding ordered pair. This is very easy to do, but very important. This is number 10. It has g of 0 is -7/9. What is the ordered pair? In other words, from this expression, what is x and what is y? What number is x? No. Look back at one of these other problems. 0 is the x. What it's equal to is the y. This whole thing is y. So in this notation, the number in here is the x, and what it's equal to is the y. So what would it be as an ordered pair? 0, -7/9. Function notation as an ordered pair. This is your x, and this is your y. Let's look at 11. Number 11 says, if f of -8 equals -6, write a corresponding ordered pair. All right, what will the ordered pair be? -8, -6. And what you have to remember is that this number is the x, and this entire value is the y. It acts on x, it gives you y. Now, number 12 is an easy question with kind of a challenging way to write the answer in MathLab this time. We've had this question before. We had it back in Chapter 7. What is the domain of this function? And it is h of x is 1 over x minus 3. All right, domain is what x can be. Well, when we were in Chapter 7, what we really did was tell people what x couldn't be. What did you answer in Chapter 7? Didn't you say x can't be 3? In fact, wasn't that your first question on your Chapter 7 test, although it was a little more challenging than that? In this particular lesson, they ask you to type in your answer in interval notation. If you took Math 307, you did a little bit of interval notation when we did inequalities, and it was, in about section 2.7 or 2.8 at the very end of Chapter 2. And then you haven't seen it since then, and some of you may not have ever seen it. So I'm going to talk about it a little bit. It's the only question in the lesson like this. Interval notation. Interval notation says from what x to what x represents this set. Do you agree that it is everything but 3? All right, so I'm going to draw a picture. Here's a number line, and here is 3. If somebody said, well, what can x be? We'd say, well, it can't be 3, but it can be everything this way, and it can be everything that way. It just can't be 3. Does that make sense? That's a pretty blue picture of the domain. Now, when I name it in interval notation, I think of interval notation sort of like a from and a to. What can x be? Well, it can be, what's out here? Yes, negative infinity. And what's out this way? Positive infinity. And if you haven't drawn an infinity lately, it's kind of like an 8 laying on its side. There really are 2 intervals here. There is one interval that represents this piece, and then there's a break. Right there is a break. And then there's an interval that names this piece. So let's name the left piece. It goes from negative infinity and it stops at, okay, somebody says it stops at 2. Well, what about 2.5? What about 2.7? What about 2.999999? I can just stand up here and say nines forever. In other words, it goes almost to 3. How do we say almost to 3? Well, in interval notation, what we do is we put a parenthesis there that says not including 3. And we never include infinity. For those of you who happen to remember, if 3 had been included, you would use a square bracket. But we use parentheses. That means from negative infinity to 3, but 3's not included. Okay? And then there's a gap. And then you pick up, and what's the other interval? From where to where? From 3 to positive infinity. We always put infinity in parentheses, and because the 3's not included, we put it in parentheses. Between the two, we put a U for union. So now let me summarize what this is. This is the domain. This is interval way of saying everything but 3. From negative infinity to 3, but don't include 3, or from 3 to positive infinity, but still don't include 3. That means there's a hole at 3. It's a very complicated way of saying don't include 3. How would you type this in MATLAB? Well, in the toolbar, you will find an infinity symbol and you will find a union symbol when you do this question. So you'll do parentheses, you'll type a negative sign, you'll click the infinity symbol, comma, 3, close, click the union symbol, and so on. They're all there. It makes an easy question hard to type in, but you only have one, and it's like this. Okay, moving on. Number 13. This is number 13. There it is. It says, if a function is evaluated at 9 and the value of the function is 4, write this situation using function notation. So what I want to do is write it in function notation. I want to say f of something is something. If it is evaluated at 9, where does the 9 go? Right inside the parentheses. F of 9 means that you're evaluating it at 9. You're plugging 9 in. If the value of the function is 4, then it equals 4. You haven't probably seen this language before. So if you didn't get it right away, that's okay. But when it says evaluated at 9, that means that that is the x value. And when it says that the value of the function is 4, that's the y value. And that's exactly what it wants you to type in. F of 9 is 4. Now, I don't know what the formula was. I don't know how they got that. It doesn't matter. It's just, do you understand the language? Well, hopefully. Okay. Now, this next question, number 14, I honestly don't know how it really fits in. And I'm not really sure why I picked it. But I did. It says, the graph of a function is shown to the right. Write the coordinates of the lowest point of the graph. Okay, what are the coordinates of that point? Yes, -2, 4. And that's all you want, -2, 4. Now, something that it does not ask, it does not refer to at all, is how would you write this in function notation? I'm just asking. MATLAB isn't asking. F of what of negative 2 equals 4. That's just for free. That is not part of the question. And that is it. For 3.6, it's all about functions, domain, range, function notation. Anybody have a leftover question? There's very little calculation in this lesson, just a couple. Okay, the ordered pair that names this point, starting at the origin to get to it, it is negative 2, positive 4. So it is the x direction and then the y direction. Whoops, I'm so sorry. So from the origin, it is left 2, up 4. Okay? And if you need some refresher on the graphing, you'll want to go back to chapter 3. Okay, so I'm going to stop this.